So good evening, everyone, or good morning or good afternoon, depending on where you are joining from. And I am Ravindran, and I head the Robert Bot Center for Data Science and AI in IIT Madras. And I welcome all of you to the AImpact Seminar series. Before we begin, just a quick introduction about the Robert Bot Center for Data Science and AI. And so we are an interdisciplinary research center at IIT Madras, funded by Robert Bosch. And so we have been in operation for the last 3 years. And the vision and mission of the center is to achieve global prominence in AI and data science research with significant societal impact by carrying out foundational research and creating top quality engineers. So we work in many fundamental areas of AI, ranging from deep learning, reinforcement learning, causal modeling, and reasoning, and so on and so forth. And we also work in applied research verticals. Right now, we are looking at manufacturing analytics, financial analytics, smart cities, systems biology, and healthcare. And we run several quality education programs and also are involved in many societal impact projects. And we collaborate extensively, both with government bodies as well as with private players, many corporates. And you can see that the list is pretty extensive. For more details, you can look at our webpage. And we are also very actively involved with the government and other NGOs in terms of socially relevant projects. We work with the government both on capacity building, R&D, and also with players like Google AI and an NGO called Arman on helping pregnant mothers or looking at preterm birth prediction, and in an effort jointly with THSTI, funded by the government, and as well as other bodies such as the Bill and Melinda Gates Foundation. And we work with Chennai Ambulance in order to help enhance response. And we have been doing a lot of work currently with COVID-19 analytics and trying to help understand how the disease could potentially progress. And excuse me, I'm just letting in a few more people into the meeting. So with regard to research and education, we are involved in various initiatives. So in fact, IIT Madras was the very first IIT to launch a 5-year dual degree program in data science. This is a program which the students get into after their +2. So basically the admission is through JEE. And at the end of the 3rd year, they opt to continue on for a 5-year dual degree program, in which case they earn a master's in data science with a bachelor's degree in whatever engineering discipline they enrolled in initially. And we also run a certificate in technology and management. It's a blended mode, mostly online and with some in-person classes and on-campus sessions along with IIM Bangalore. And we run several summer and winter training programs for specific organizations and also for a larger body. And we have multiple workshops and industry conclaves, which we periodically will be putting out calls for participation. And I hope that some of you will be able to participate in many of the future events. And we have several outreach and scholarships, and so we have a postdoctoral fellowship, RBCDSI postdoctoral fellowship, which is very high value and also gives significant independence to the postdoctoral fellow. And we have something called a post-baccalaureate fellowship, which right now we are having a lot of application, a lot of interest, especially in the COVID situation, where people are more interested in exploring research right after their bachelor's, but they're not really ready to commit to a long-term research program. So the post-baccalaureate fellowship allows them to explore a research career for about a year or two, and then decide what they want to do with their future. And we also have a lot of other ways in which people can associate with the center in terms of research experience program, the associate researcher program, and the visiting researcher program. You can look at our website for more details on these and other ways in which you can engage with our center. And here you have the website, the URL, and we are also on all social media, and you can find us there by looking for RBC DSI on any of these social media. So finally coming to the goal of today's seminar. And so, like I said, RBC DSI is involved in a lot of cutting edge fundamental research, and we decided that we are going to showcase some of the high impact work that is coming out of the center. And so recently, so a paper published from the center got a best paper award in one of the top computer vision conferences. And so today, so we are presenting to you the work on ablation CAM by Saurabh Desai and Harish Guruprasad. Saurabh was a project associate with the center. Saurabh was a project associate with the center while he was engaged in this work, and currently is a graduate student at Oregon State University. And Professor Harish Guruprasad is a faculty in the computer science department who works a lot, works in optimization and foundations of machine learning algorithms. And Harish finished his PhD at IISc and has been with us for the past 3 years. And I'm going to hand over to Harish. So Harish will start off by introducing the area of research, and then Saurabh will talk about the specific work. And Harish, I'm handing over control to you. Just give me 1 sec. And Harish, please take away. You can share your screen. I'll automatically stop sharing.
Oh, okay. Hello, everyone. Can everyone hear me?
Yes, I can hear you.
Oh, okay. I'll just do the share screen. Yeah. Okay, so welcome everyone to today's start of the lecture series. So my first question is, how do we pronounce this lecture series? Is it impact or AI impact, or I don't know, an impact? So that was my first question when I saw the name, and it's something to think about during this talk. Right? Okay, so with that silly joke out of the way, so let's begin my talk. So today's talk is mainly headlined by Saurabh. I'm basically the opening band, opening neighborhood band before the Beatles. So that's keep that in mind, right? So today, my goal is just to give you a broad overview of what interpretable AI and visualization of the neural models looks like, and not really go into any details. Right? So feel free to stop and ask me questions. I don't know if I can see the chat. Chat is too slow. Can others unmute themselves? I don't know. I was not able to unmute myself when I was talking, so I think it's I don't know if others can. Not an expert at Zoom, so I'm still figuring things out here. Okay, I'm admitting some people. That's the easy part. Okay, so everyone is muted. Okay. So in that case, what we'll do is I'll occasionally high impact with the H silent. Okay. So what I'll do is I'll occasionally stop and let people ask questions in the chat, or I think I should be able to unmute others. Okay. Yeah. So if you have a question, you can. I think you can raise hand or something like that, and I can unmute. We'll do that. So occasionally I'll stop and ask for questions, and that's the time when you can raise your hand, and I'll unmute. Okay. So with that out of the way, let's begin the talk. Right? So this is the broad outline of my talk now. So I've broadly divided into 4 sections. The first section is just general funda on why do we need interpretability in AI. So I took a brief look at the audience, and this audience does not really need much convincing that you need interpretability. I'm sure a lot of you have read a lot of these papers and know what's happening, but still I'll go ahead and give a brief overview of why you need interpretability in AI. And then I'll go on to give a brief overview of what kind of models are we looking at. So the title is mostly is neural models. I've given some non-neural models also here so that you can see some contrast. And then I'll give some brief overviews into some interpretability paradigms that are really popular. And then finally, I'll end with a caveat, which is, I'll end with a caveat. So, okay, so what's the need for interpretability in AI, right? So let's imagine this scenario happening, let's say, 10 years from now. Right? So you go visit your family robot doctor, and the robot doctor says you're likely to have a heart attack within a month. Hopefully, it's not true, but and then you're shocked, like saying, hey, what? Why? And the robot doctor is known for his accuracy, and he says, it's because your blood pressure into the top right pixel of your X-ray plus sugar level minus sine of BP squared is greater than 45. That's the reason why you're going to have a heart attack. And you are probably not going to be very pleased with this. You might be right, but that does not convey anything to you. So you want, as a patient, you want to know interpretable reasons like why does the robot think that you're likely to have a heart attack, and what can you do to prevent it? Right? So the accuracy alone is not really useful in this situation. So you don't want to just know you're going to have a heart attack. You also want to know why and how you can prevent it. And for all those reasons, interpretability is really important. So let's go for another example. Right? Let's say you have a surveillance bot on the streets, which is say flagging potential security risks. So, and you are a police guy, and you just look at video feeds, and suddenly it flags, let's say, some 3 people, and you've detained them. And now it's their legal right to ask the reason, why have I been detained? And as a police guy, you are required to obey civil rights, and you should say why that happened. Right? If the machine just puts some saying that these people are security risks and says nothing about that, even if it's 100% accurate mission, and if it has identified all past terrorists with 100% accuracy, it is not really going to be useful in that particular scenario. So you need a model which speaks the human language as well as, at least as much as possible, while being accurate at the same time. Right? So that's another example of the reason why you need interpretability, because there might be, you might need to explain the reason to someone else also, not just have a case. So, and there are several examples. I'm going to give just a few examples to just impress upon the fact that interpretability is as important as accuracy in some situations. So let's move to another example. Let's say you are a data scientist in some agriculture startup, and you've built up a data set of healthy and diseased leaves. Right? So this is what you have built up, and you've trained a revolutionary neural model which achieves 100% accuracy on the training data, and it's perfect. But when deployed in the testing setting by farmers, it's just completely wrong. If this is just a scenario, you will never be able to say why it's happening. Right? I mean, it's not overfitting, because you do the as far as the data science is concerned, it's not overfitting, because you have split the training data into train and validation, and your model performs just as well on validation as it does on training data. So you still don't know why this is happening. Right? I mean, you would ideally like to know what's happening. And in this case, I made it very obvious here what's happening here. That is, essentially, it so happens that all the healthy leaves were photographed in highlight, and all the diseased leaves were photographed in low light. Right? That's how the training data looked like. And so essentially, your model got really good results really quickly by just focusing on the average brightness levels. Right? So that's what it did. But on the test data, you have an example where I have an image where it is really bright, but it actually have a diseased leaf. Right? So in this case, it will just focus on the brightness and say that it is a healthy leaf, but clearly it is not. Right? If you had an interpretable model which said why I'm making this decision, I'm saying this leaf is healthy because the average pixel intensity is greater than 200. That's the reason you are saying that, then you immediately know why that's happening, and you can go and debug. Right? So debugging is another important reason why interpretability is important. Right? It's not just, accuracy on the training data and the validation data is one thing, but why you are getting that accuracy, and because the real world test data might not be the same as your test data. So for example, in this scenario, you had your data scientist, your company had a buggy data collection procedure where it gave 2 different people to collect healthy and diseased leaves, and it so happened that the healthy leaf guy had a better camera and had a better lighting system, but the guy who's photographing diseased leaves had maybe a worse camera and had photographed in low light system. So because of your company's faulty data gathering mechanism, that bug crept in. And it would be nice. I mean, ideally, it should not have happened. But now that this has happened, it would be good to for the model to also tell why this is happening, and so that you can debug it even at a later stage. Right? So that's another application for interpretability, right? Debugging a learned model. So there are several other examples, but this should give you a general idea of why interpretability is important and beyond accuracy. So that's what are the broad goals of the interpretability, right? So that's first, in most situations, you'll find that there is an accuracy interpretability trade-off. That is, you'll find that very simple models are very interpretable, but they don't have a very good accuracy. And the more complex the model becomes, the less interpretable and more accurate it becomes. So, and that seems like there is an accuracy interpretability trade-off, and you want to be on the right point in that curve. And there are two broad goals in an interpreting a neural model, which is first to get a general philosophy of the model, and secondly to get a precise explanation for a particular prediction. Right? So let's take for example the doctor example. You want to know what the broad philosophy of the robot doctor is. I mean, you want to know whether maybe he takes a look at the MRI images first, and then he decides what to do with the blood levels and all that. So you need to know what the general philosophy is, and he's not just doing a horoscope business, right? So you need to know that, and beyond that you need precise explanations, right? So why this particular patient is likely to have a heart attack in the next 1 month, you want to know that also. So that's more to the point, and both these goals are valid and both these goals are important. And this particular interpretability problem is not new by any means. It is almost as old as machine learning itself. And for example, some of the oldest machine learning models are speech models using probabilistic speech models like hidden Markov models. And you can use simple, fully observed models for speech, like Markov chain models. They are fully observed and you can interpret them very easily. Where, for example, x1 is the sound waveform for the first second, x2 is the sound waveform for the second second, x3 is the third waveform for the third second, and so on. You can have this kind of a Markov chain model where you can say that the sound emitted at the second, let's say millisecond. The sound emitted at the second millisecond depends only on the sound emitted at the first millisecond. Or you can say that the sound emitted at the third millisecond is independent of the sound emitted at the first millisecond, given the sound emitted at the second millisecond. Right? So this is the kind of Markov chain assumption, and everything here is observed. Right? So you observe the waveform at the first millisecond, you observe the waveform at the second millisecond, you observe the waveform at the third millisecond. So everything is observed. It's a fully observed model. Right? It's a nice model, and you can interpret it very nicely once you have learned the parameters. But the problem with this is these don't work at all. They are not very good for doing any kind of modeling or speech generation or any kind of process. And generally, people find that the latent or hidden variable models improve performance significantly. Right? So, and as I mentioned, hidden Markov models for speech is a classic example. And the hidden Markov models immediately add an extra layer of complexity. That is, you have the observations, you have the sound waveforms emitted at the first millisecond or the second millisecond or the third millisecond and so on. But you also have unobserved variables. That is, for example, you think that what syllable you spoke at the first millisecond decides the waveform at the first millisecond. What syllable you spoke at the second millisecond decides the waveform at the second millisecond, and so on. Right. So that's the assumption under which you designed this model, and said that the syllable at the second time step depends only on the syllable at the first time step, and so on. So that the waveform emitted depends only on the syllable spoken at that particular time step. That's the assumption here. But the problem with this is you don't have syllable level data. You only have waveform level data, which means that all these syllable variables are hidden variables. You can learn them still. There are algorithms for learning these models. But the problem is they are not interpretable anymore, because you don't know what you think these represent syllables, but they need not even represent syllables. They can be something else. You don't know. For all you know, they don't even need to represent syllables. But in practice, they do seem to represent syllables, but they can be anything. Right? So the interpretability goes out the window the moment you have hidden variables. There is variables that are there for increasing the modeling power, but you cannot say a priori what these symbols mean. Right? So what this variable mean, as opposed to the fully observed model case where you knew exactly what x2 meant. x2 is the waveform emitted at the second time step. Right? So you knew that. But s2 is something, it's just a hidden variable. You think it corresponds to the syllable at the second time step. That may not be true. So the interpretability goes out the window the moment you have latent variable model. So this is a well-known observation, well-known issue with machine learning models. But still, people use hidden variable models mainly because they are very good. So that's the reason why people use that, even with the loss of the interpretable models. So the problem with interpretability does not start with deep learning or neural networks. It goes way before that. The main problem is with hidden variables. That's the thing that I want to impress upon. So with that, I think we can have maybe a small question session. So do you have any questions on why the need for interpretability in AI and things like that? So if you have any questions, maybe you can say something in the chat and I can unmute you. Okay, I'm admitting more. Chat. Okay. So there is a facility to raise hand. So if you have any questions, feel free to raise hand, or you can send a chat message also. That's also fine. Okay. So Arun has asked the question, is there a formal definition of interpretability? The answer is no. There is no formal definition of interpretability. Interpretability is, I mean, it's really, there are a couple of slightly more formal frameworks of interpretability than others, which I'll broadly touch upon later. But yeah, I am admitting people in the video. Yeah, so that I think we can move to the next section, which is I made this correction. It's machine learning models. So what kind of machine learning models are we looking at? So that's the next. So, yeah. So if you have questions, you can ask after the second section. Well, there are several machine learning models. I'll just touch upon a few of them to get an idea of what all are possible. So the first class of models are the simplest, the linear models. And here the output is simply a linear function of input. These are the ultimate in interpretability. These are the gold standard, I would say, for interpretable models, because you can just read off and interpret what it means. For example, if you have a model which says that heart risk is equal to BP minus 120 plus sugar minus 100 plus 10 times cholesterol, you can immediately see the model and immediately understand what's happening here. You can understand, okay, BP and sugar must be kept low, around 100 or 120, and cholesterol, keeping cholesterol low is much more important, right? So you can immediately see this and understand what's happening here, and the interpretability, I mean, the model tells the complete story as it is. So that's the gold standard as far as interpretability goes. And if you had linear models, if you had only linear models, there's really nothing left to do. It's a done thing, right? I mean, interpretable. All linear models are by definition interpretable. So that's the easiest thing that we can think of. The next class of slightly more complex models which are interpretable are perhaps trees. So here is a toy example of classifying houses in either as belonging to San Francisco or New York. So that's you have a bunch of features for each houses, like elevation, price per square feet, number of bedrooms, number of bathrooms, and so on. And the goal is to classify whether that house is in San Francisco or is it in New York. Okay? So that's this is a two-level decision tree that has been learned, which is essentially saying that if elevation is less than something and your price per square feet is less than something, then it's a house in San Francisco. If the elevation is greater than something, elevation is less than something and price per square feet is greater than something, then it's New York. And similarly, if elevation is greater than something and price is greater than something, then if the house is in San Francisco. If elevation is greater than something and the price is less than something, then it's New York. So you can immediately, this also is reasonably interpreted, right? So if someone, if this model predicts a particular house is in New York, you can ask, why do you think my house is in New York? The model can simply say, it's because your elevation of the house is less than 100 feet and your price per square feet is greater than $1 million. So that's the reason why your house is in New York. So he can look at it, whether it's right or wrong. The user can look at the reasoning and say, well, yeah, I can understand your reasoning. It happens to be true or it happens to be false. I'm reasonably satisfied with it. So that's the use of trees are also intrinsically interpretable to a certain extent. Not as much as linear models, because you can easily have trees of depth 20 or 30, in which case it's no longer going to be interpretable. So low depth trees are indeed interpretable. So that's another simple interpretable model. So with these two, and there is one other example which I wanted to mention, I didn't have the time, didn't have the opportunity. Let's skip that. Right? So with these, we'll move on to the non-interpretable models after these. So the first non-interpretable model that I'm going to talk about is the simple multilayer perceptron. Right? So you have a feature vector, which is the input, and you have a bunch of hidden layers, and then you have the output layer. And immediately you should see that the culprit really comes from the hidden layers. Right? So the moment you have hidden variables whose meaning you don't know a priori, right? I mean, they are there as simply as a tool for representing a more complicated function. That's it. They are just an intermediate object. You don't really know a priori what, for example, this particular blue circle means. You don't know that. So that's the moment you have such hidden layers, the interpretability goes out the window. You can no longer say this, but even if you have a 100% accurate model, it's no longer possible to intrinsically interpret this particular model. So that's multilayer perceptrons, and you can have the next kind of networks that we are looking at is CNN. CNNs, if you don't know, CNNs are really, you could view them as specialized multilayer perceptrons which have extra constraints on the neurons. Essentially, it says that each neuron does not depend on, depends only on a given neighborhood. For example, this particular neuron depends only on these other neurons, right? So I forgot to mention, each of these hidden layers or output layers or input layers, we'll just call it as neuron. So here in a CNN, you'll have, let's say, each layer is going to have channels as well as first layer can have 24 cross 24 cross N1 channels, right? So that's essentially 24 and 24 into N1 neurons. And each neuron really, unlike the MLP case, does not depend on arbitrarily on any input. For example, this particular neuron depends only on this region of the input space. Similarly, this particular neuron depends only on this region of the input space for the first layer, right? So that's the advantage that, in a way, this is slightly more interpretable, the model, because you can view them as filters doing convolution. So that's slightly more interpretable, but it still has the same issue as multilayer perceptrons. That is, there are hidden variables, hidden layers which are not intrinsically interpretable. You don't know a priori what this particular filter means, right? So here we will call each channel as a filter, right? So that's fine. That's CNN. And there is another class of models which have become really popular, which are attention models. So attention models can be really complex, but I'm just giving the core attention models. Here's a core example of what an attention model is. It's based on a simple idea that you might have a large input, right? For example, here you have, let's say, 1,000 cross 1,000 image, right? So you could have a huge image, but you know that this image is either a cat or a dog, and you also, let's say, you also happen to know that the cat or a dog is small, right? It means that it's not going to occupy the entire image. So you can artificially say split the image into, say, 9 sub-images, and you know a priori that the cat is going to lie in the cat or the dog is going to lie in one of these 9 sub-images. It's not going to span the entire thing. So that means that the whether this particular image is cat or dog does not depend on the entire image. It depends only on a part of the image, but you don't know which part. That's the rub here. You don't know which part, but you do know that the class of this image depends only on a part of the image. So that drives you to another kind of approach, which is typically the attention model. So what it does is, for example, in this case, you've broken this image down into, say, 9 sub-images, and you have a focus block, which essentially operates the same block which operates on all the 9 sub-images, and simply says, essentially captures whether the object, either cat or dog, is in this particular block or not. That's the only thing this focus says. It does not try to say whether the image is a cat or a dog. It tries to only say whether there is an object in this particular block or not. So that's why you have 9 blocks, each of which is, say, going to give a scalar, which essentially measures how likely is it that there is an object in this block. Right? So that gives you 9 scalars, and effectively say what's the ideal case scenario. Ideal case scenario is that you will find that the focus 1, 2, 3, 4 will essentially say no, there is no object in this image, or it will give like a very small scalar. And focus 5, which really has the cat, will have a high value, let's say 10 or 20, and then focus 6, 7, 8, 9 also is going to have small values simply because there is no object there. Right? So that's the ideal case scenario. And if you have such a case, and then you can just use these as weights to combine these images. So what would happen then? You would, for example, in this case, you would have something like 0, 0, 0, 0. Then you have, let's say, 5, 0, 0, 0. Right? So that's what you would have. You can essentially use these as weights to combine these 9 smaller images. Right? So these are now smaller images. And if you use these weights to combine 0 into this block, plus 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 5 into this block, plus 0 into this block, and so on. You have this, now you have a new image which is smaller in size. So that's the idea here. That's what the combined part does. And then now you have a smaller image. It's a lower dimensional problem, and the classification can work on this instead. So this is the core idea of attention models. There are multiple extra bells and whistles that you can throw in. You can have multi-head attention, you can have sequences and so on. But the core idea is just this. That is the output of the model depends only on a part of the image. It does not depend on the entire image. It depends only on the part of the image. You don't know which part though, and that part is which part of the image to focus on, which part of the input to focus on is given by the focus module, and then you use that to combine all these smaller blocks into a one block, which you can use the standard classification. Of course, you could just ignore this entire thing, and you could run the classification model directly on this image. Right? The problem with that is your classification has to work on a 1 megapixel image instead of a smaller thing. It has to work on a higher dimensional problem. The hope is that in this particular assumption, using this fact that the output class does not depend on the entire image, but rather only a part of the image, helps in improving accuracy significantly. Right? So that's essentially, this is a general principle in ML. That is, if you know some prior information about how the data works, it's always good to incorporate it. In this case, there is some prior information, that is the output class depends only on a part of the input. Using that helps. So that's attention models. I'm focusing on this. I'm giving extra attention to attention models simply because this is slightly more interpretable than the other models. Right? So we'll come to that later. So finally, you have RNNs, which I think we'll skip. So I think I'm going over time. So I'll skip now. Let's just briefly overview RNNs. RNNs are a sequential model where you have a sequence of inputs. For example, these x1, x2, x3s could be either words or words in a sentence, or speech waveforms or something like that. So that occurs naturally in a sequence. And you have a processing block here, which essentially combines the initial state and the current input into a new state. Right? So your H0 and your x1 is combined into creating a new state. Ideally, this H1 summarizes x1. Similarly, H2 summarizes x1 and x2. H3 summarizes x1, x2, and x3, and so on. Right? So this green block, essentially, you can just view it as a black box, which takes in the previous state H2 and the current state x3 and gives the current input x3 and gives the current state x3. Right? So that's this particular block. Ignore the outputs wise for now. So that's the goal of the RNNs here. So we'll come to that later. Okay, so with that, I think we've given a brief overview of the neural models. If you have any questions, please raise hand or. How do I do that? Yeah, so Arun has asked the question whether models like word-to-vec be considered interpretable. It's a word-to-vec by itself, it's a model, and it by itself is not interpretable. So I'll give an example of these kind of things where you have a model by itself, it's not intrinsically interpretable, but you can do reverse engineering to make it interpret as much as possible. So that's the, I'll give an example. I'll not give word tweak exactly, but there are, I mean, even standard models like RNNs or CNNs, if you dig deeply enough and do enough reverse engineering, you can try to interpret some of it. Word tweak is also in that category. So the model is not intrinsically interpretable, but you can interpret it if you do enough reverse engineering. Okay, so Rajan asked the question, interpretability versus explainability. I actually don't really know about this. So that's anyone. Yeah. So Rajan asked the question whether what's interpretability versus explainability. They are reasonably similar in my opinion. So there might be some subtle issue, subtle difference, but I think they are very similar. I don't know the difference. Yeah. So okay, where does SVM fall in the spectrum? So SVM is an algorithm, right? So SVM is not a model. So if you are using SVM to learn a linear model, it's a linear model. So you can interpret a linear model as easy. Right? For example, let's say you want to you want to learn a model for heart risk based on blood pressure and sugar and cholesterol and so on. And if you learn a linear model uses these things, then use SVM to learn a linear model, the final output will still look like sugar minus 120 plus blood pressure minus 100 and so on. Right? So it's still a linear model. But SVMs also can do kernels, and with kernels there is a different kind of interpretability, which I will mention in another paradigm. But generally, kernel SVMs are harder to interpret than linear SVMs. So it's interpretability and reasoning related. Okay. You definitely have to use reasoning to interpret any output. So I don't really know what reasoning is, other than the general common noun reasoning. I don't know what reasoning is in the context of machine learning. Okay. So I think if there are no more questions, I think we can move to the interpretability paradigms. Okay, so we'll move to the interpretability paradigms. The first thing is simple intrinsic interpretability. So you can have linear and small depth free models are intrinsically interpretable, as I mentioned earlier. But it also happens that simple attention models are also interpretable to an extent. Why is that? Because let's go to the attention block again. So even though you have each of these modules or classification modules could be really complicated. Each of these modules could be a CNN. Each of these focus modules could be a multilayer perceptron, or each classification module can also be a multilayer perceptron. But there is a key thing here, that is you can interpret an intermediate output here. That is, the output of each of the focus modules can be interpreted. So if the focus one module is simply the score of whether the top left is contains an object. Right? So you can interpret the output of this particular focus module, even though you can't interpret the intermediate objects in the focus module. So that's that gives you an extra handle on interpretability over standard multilayer perceptrons, where you have just something like this. There is no way you can interpret any of these blue nodes, but or even in CNNs. But here, in attention models, you can interpret the output of these focus modules, and that makes life a little bit easier for interpretability. Right? For example, you can use attention models for generating, say, caption image. So here is a couple of examples. So this is the green, the grass image is an image of a woman throwing a frisbee, and that's actually the caption. The caption generated by the model is a woman is throwing a frisbee in a park. Right? And you can each word is viewed as a classification problem with given the previous words. So you can just say focus on the 1, 2, 3, 4, 5, sixth word. The sixth word happens to be frisbee, right? So you can ask for classifying the sixth word as a frisbee. Why did you do that? I mean, you can ask the model, why did you classify the sixth word as a frisbee? So the model clearly cannot interpret the entire outputs, but it can interpret the output of the focus module outputs. So, and if you do that, for example, in this case, what's done is, I think the image is split into 16 sub-images. and each subimage gets a focus module. So which means in this case, it so happens that the focus module corresponding to this particular block, I think it's the first, second, third, fourth, the fifth block. The fifth block happens to be high, which is nice in the sense that that is really where the frisbee is. So you can see that you can interpret a question like this. For example, if this particular image, this was the caption that was given, a woman is throwing a frisbee in a park, you can ask a question like, why did you say frisbee? The model can output this particular image. It says that I said frisbee because this was the part of the image I focused on for giving this particular word. So this is slightly interpretable, so you can go ahead. Similarly, here's another example here. A dog is standing on a hardwood floor. You can ask, why did you say dog? And it can focus on, it says, I said dog because I focused on this particular part of the image. So this is not fully satisfactory because, for example, you can't ask, why do you say standing or why do you say throwing? Because verbs don't really have a presence in the image, but this is still better than nothing. If you had just a black box model which just took an image and output a sentence, there is no way you can see anything. Here, because you have a handle on at least an intermediate output, you can ask the question and it can give reasonable answers for reasonable questions. And one other example is, as I said, you can use these interpretable models for debugging. And that's true. For example, you can take this third image here. Here, this is the image that was given, and the caption that was given is a woman holding a clock in her hand. And this is clearly not true. There is no clock in this image. But you can ask, why are you saying? You can ask the model, why are you saying clock? And it will say, I said clock because this is the part of the image I focused on. And you can immediately see what's happening here. It saw a circular pattern, and it immediately assumed it was a clock, which is a reasonable thing to say, but it gives you an idea of why a model fails also, and you can potentially use this for debugging the model, but that's not the goal. That's not the immediate goal. The immediate goal is to understand why this particular prediction was made, and interpretability and attention models can do that to a certain extent. So that's why I've separated out attention models from other neural models, simply because there is an intrinsic level of interpretability to attention models. Of course, you can have super complicated attention models like Transformer or BERT or so on, in which case they also lose the interpretability a bit, but it's still more interpretable than standard models. That's the so here I think I'll stop for more questions along the way. So because I'll go through several widely different topics, I think it's good to have questions as and when. So if you have questions, please feel free to ask in the chat or raise your hand. Okay, so if there are no questions, we'll move to the next. So the next paradigm is what I call as reverse engineering. I don't know if people in the interpretability literature actually call this, but reverse engineering. But it really is reverse engineering, right? So imagine, for example, you're like a kid and you got a working radio when you were so you don't know what the radio is doing, but you do have a screwdriver. You can go ahead, take it apart, and see what part does what. You can short circuit certain things, you can power off certain things, and so on, and you can see what works and what doesn't work. And you can, even though you don't understand the full electronics of how a radio is going to work, you can have a reasonable block with block understanding of how the radio is working using simple reverse engineering. Right? So that's reverse engineering is probably one of the most powerful tools that science has given us, and it's only natural that we apply that to something like RNNs. Right? And the problem with that is obvious immediately, that is it's a very labor intensive task, right? You have to go inside the model and understand what each block does. And typical deep neural networks are more complicated than a typical radio or a watch, right? So that's, it's going to be much more difficult, but it is possible to do if you put in enough effort. For example, here is an example. So this particular RNN as a sequential model was trained for predicting the next character given the previous character. Simply a simple character RNN, and that's the it was trained on I think warranties, and that's the first model. The second model was trained on the Linux kernel, right? So you have two models, both of which are character RNNs. That is, seeing the previous characters, you want to predict the next character. That's the goal of these character RNNs. Yeah. Okay. Right. So I'll ask these questions. So this is a simple RNN model which takes in a a character. It's a character level RNN model that predicts the next character given the previous characters. That's the model here. And you can see that certain units of the RNN behave in very nice fashions. For example, there is one particular unit in an RNN which essentially behaves this way. So recall the RNN model. I'll go back to the RNN model just once. So you have the RNN model H, right? So the H essentially is a vector which captures all the information till now, right? So that's what H is capturing. And you want to interpret H is, let's say, a 100-dimensional vector. You want to interpret each of H, the 100-dimensional vector essentially captures all the previous relevant information until that particular point. For example, H3 is a 100-dimensional vector. It captures all the relevant information till word 3. If you have War and Peace is, I think, 1 million character text, which means that the H 100,000 essentially captures the information about all the previous 99,999 characters. Right? So you want to know what information is it actually capturing. So what information is useful for predicting the next character, right? I mean, obviously it only needs to capture information that is useful for predicting the next character. That's the goal here. But you still have these 100 numbers that summarize the first, say, 100,000 characters. You want to know what these 100 numbers mean. And you can do so using painful experimentation. And for example, people have figured out that certain networks have certain units in that hidden state are essentially sensitive to position in line. For example, here you have one hidden unit which essentially tracks how far are you from the beginning of the line. Right? So you can see that how far here you can see that it's blue means low or red means high. So essentially that particular cell is tracking how far you are from the beginning of the line, and you can see that it gets red as it goes further to the right, and immediately it gets blue as the next line begins. So it's kind of it tracks the beginning of lines. I mean, how useful is that? We don't know, but it tracks that. And another useful, for example, you can run the same model for the Linux kernel, and you find that a certain cell actually tracks whether the current character inside an if block or not. For example, you can see that it's mostly blue, but the moment you have an if block, it becomes activated. It becomes red in the if block, and once the if block closes, it becomes deactivated again. And once the if block becomes, essentially it tests the condition. So these are interesting things, right? So this is a logical thing for you to do. If you are building a code which is building a network which interprets code, it is natural that it looks at if classes differently, it looks at for loop classes differently, it looks at functions differently, and so on. Right? So, and you can find certain cells which do that. So that's one way to interpret it, but you can immediately see that this is a really, really painful way of doing things. You have to go through all the hidden variables and see whether they mean anything meaningful. And they have found that most of these cells are actually meaningless. Only some of them, I mean, meaningless to us humans. It is useful for predicting the next character, but we can't interpret those cells. But you can, if for a certain cells, you can do enough reverse engineering to understand what's happening. So this is exactly the same kind of understanding or interpretation interpretability that we can get for word to vec. So word to vec by itself just gives a word vector for every word. It is not by itself interpretable, but if you put in enough extra effort into it and find out whether king minus man plus woman is equal to queen. So this is not really intrinsically, word to vec does not output these equations to you. So you have to find out, you have to know that king and queen are the male and female versions, and king minus man plus woman equal to queen is a meaningful thing to do. Right? So this is something which the reverse engineering people have done, and see whether this particular model makes sense or not. The model by itself is just a model. All interpretability effort is something which comes from the user. So that's the so this is reverse engineering, which is it's a very powerful tool, but at the same time it's very painful and not very generalizable. If you have some other new model that comes up, you don't know whether all these features are going to even appear again. But this is something which you should have in your toolkit when at least for small scale experiments. So I think I've got a couple of questions here for the attention model. Okay, so yeah, Pranjal asked the question, if for the attention model, if element is not fitting in small frame, then how to interpret? The answer is typically I've made a very simple partition of the image into 9 blocks, but you can have overlapping blocks. You can have overlapping blocks where the 9 blocks are, you can have multiple blocks which are overlapping each other. So in a way that you can have, but of course, if you might have a situation where the object is big enough to occupy the entire image, in which case the hypothesis is true, not true. So yeah, in that case, attention models might not work. Right. Srijan asked the question from when looking at CNN/ANN, can we disable certain filters and nodes, and based on the change in output, infer the reasoning behind the decision, determine the influence of filter/node on the output? Okay, so Srijan, did you read the AblationCAM paper? So this is exactly what we do. So you will see Saurabh talking about this in his talk. So it's a very good question and a very nice idea. So this is exactly, a variant of this is what we do in the AblationCAM. Okay, so with that, I think we can move to the next thing. Yeah. So the next paradigm is feature visualization. So we'll do that for CNNs. You can do it for pretty much any neural model, but you can give easier, nicer pictures for CNNs with images. So that's the nicer case. So we'll do that. So here we'll take a CNN. You have a learned convolutional model, and you want to understand this particular model. How do you do that? Right? So the standard way to do is, can you visualize a learned filter? That's the goal. So how do you do that? And right now, the most promising approach is to use optimization. Right? So what does that mean? It means that you can visualize a learned filter by finding an artificial image that triggers it. Right? So that's a sentence that you need to keep in mind. For example, let's say this is let's say this is the second layer of the CNN. So this is the second layer. You have 3 filters, and you want to know what triggers this particular second filter. Right? So this is the orange spot is highlighted here. You want to know what triggers this particular second filter, and what you can do is you can just search over. You can search over all possible images and find out what particular image triggers this particular filter to the highest value. So that's a very natural thing to ask, and you can do that. And in this case, it so happens that if you one particular answer, this is the image that seems to trigger this particular filter. Why is that the case? I mean, that's a difficult question, but let's move on to example. So how do you find that image? The same way that you optimize pretty much everything in neural networks, just use gradient descent. So you start off with a random image, and you optimize over the image now. I mean, the neural network parameters are fixed now. So you are trying to just find an image which maximizes the response of a particular filter, right? So you start off with a random image, and you do your standard gradient descent. In fact, you start off with this random image, and this is the structure that you get. So it's clearly learning something. The filter is kind of capturing a wireframe of sorts, so to speak. I don't really know what it's doing, but it's doing something. It's not nice. It's doing something meaningful. But what is it together? We don't really know. So that's another way to visualize filters. This is again not a perfect way because you can't even give names to these things, but you can group these things in meaningful ways and see what happens. For example, this is what happens. You can see clearly the different nature of the feature visualizations as you move along deeper layers. As at the first layer of the CNN, you learn very low-level features like edges and ridges and so on. At the second layer, you learn slightly more complicated patterns like textures. And the third layer, you learn patterns. At the fourth layer, you learn parts. And the fifth layer, you learn actual objects. So this is the standard reason that people give for why do deep networks work. That is, you can build hierarchical representations, in which deeper layers build more and more complicated representations of the input. The first layer would just do standard edge detection, but the fifth layer would actually each filter is probably going to detect some really complex object. So that's one way to visualize features or filters. So then the question is, why do you want to optimize over hallucinated images? Because you can clearly see that these images are not natural. I mean, you would never see an image like, let's say, the image on the top right here in the real world. I mean, there is no way that many people wearing that many identical shorts are going to live without heads inside the image. Right? So such people don't exist. People without heads and only shorts don't exist. So these images are not realistic. So why, in that case, why do you want to hallucinate such images and optimize over them instead? Why not just search over the training images and just output the image which which activates a particular filter the highest, right? That is a very natural thing to do, and you can do that. And for example, let's say you did that for, let's say, a particular layer, a particular unit, you might find that these images, the top left 9 images, these are the images that show what dataset examples show what neurons respond to in practice. So if you look at just that, you might think that this particular neuron is detecting baseball. That's what you might think. But it's not really detecting baseball. If you optimize over all images, you find that this is the pattern that actually emerges. And it's really not detecting baseball, but rather it is detecting stripes. That's what it is doing. And that's a useful thing to have. Right? I mean, yeah, baseball does have stripes, but this particular filter is not really detecting baseball, but rather stripes. That's an interesting thing to know. Similarly, for example, you can have another unit and see what input in the data set maximizes that unit, and you'll find these kind of faces, animal faces. That's what you might think, but actually it's really just detecting snouts of dogs. That's what it is doing, and that's still a useful thing to have. I mean, it's the network is not really, if you just look at the data set images, you would not get a complete picture of what the neural network is doing. So that's the use of optimizing over images and not just taking the data set images. Okay. Okay, sure. Okay, in CNN, how to decide how many layers should be incorporated into the network? So that's not the goal of interpretability. Right? So interpretability is you have already learned CNN and you want to just interpret that particular learned CNN. That's the goal. Okay. So finally, we have we have feature visualization. We also have other kind of things, which is normally called attribution maps. A typical example of an attribution map is a GradCAM. Right? So I'll not really go into the math of this, but this is what it essentially does. Right? So you can ask the question, you can give this image and say, you can give the original image here and ask the network, ask the learned network, what makes you think that this image is a cat? Right? So you can ask that question, and the network can output something like this. Right? So it can say, if you ask me why this image is a cat, you are not saying, the network might output either a cat or a dog. Both are valid answers here. But you can ask the question, why do you think this image is a cat? And for that question, a good answer might be something like this. Right? So you can highlight the cat parts of the image and say, the network can say, I think this particular image is a cat because these are the regions I focus on when I say cat. So that's a useful thing to have. And this is called an attribution map. Right? So what does it do? It attributes different parts of the input to different classes or different things that you care about. So we saw this already in attention models, but you can do this. The thing with GradCAM is that you can do it even for non-attention models. You can do it for standard CNNs, and you can still get an output like this. So this is called an attribution map. I'll not really go into the details of how you do it, but the broad idea is that you linearize the model. Right? So as I mentioned earlier, linear models are the ultimate in terms of interpretability. And the main reason why you can't interpret these more complicated models is that they are not, they have hidden variables and you can't interpret them. But what if you just linearized it on the neighborhood and view them as linear models, right? So that's the broad idea. And once you linearize them, then it becomes a linear model. You can just see, okay, what all features are triggered for this particular input. So that's the broad idea behind attribution. So I think there is a very nice distill post by Crisola on how you mix, how you combine both attribution, how you combine attribution maps and the feature visualization into an interpretability building block, which I don't really think I can do a better job than he does. So I recommend that you just go here and see. Right? So I don't think, he does a much better job in a blog post. I don't think I can do that in a talk. So just please go there and take a look at it. So I'll move on to the next paradigm, which is called influence functions. Right? So we have right now been looking at understanding a neural model in absolute terms. Right? So we want to understand why are you saying this particular decision? Right? So why are you saying this particular patient has heart risk? Because this patient has high BP. Right? So that's the kind of reasoning you have been looking for. In some situations, you might not even have understanding of features. Right? Let's say, for example, you have taken measurements of, let's say, some industrial measurements, right? So you don't have complete understanding of what's actually these numbers are. What would be interesting is you say that this particular machine is faulty because this machine is similar to these machines, and these machines were faulty, right? So that could be an interesting thing to have. Right? So those are called influence functions. So that's the question, is that can you explain predictions using training data? So the answer, how do you do that, is the simple question to ask is, how would the model's prediction change on a given test point if we did not have a given training point? So that would essentially capture the importance of a given training point for a given test point. So that's the question. And there is a very simple answer to this. Just remove that training point and retrain. You can see that it's obviously possible, but you can also see this is not scalable. Right? You can't get how you might have millions of training points. You can't do this. You can't retrain for every single thing. Influence functions are simply a more computationally efficient approach for doing the same. Right? So I'm not really going to say what these are, but essentially they simulate this particular idea, which is, can you remove or repeat a sample in the training data set and retrain? And based on that, how does the output of the model change for a given test point? And does that, yeah. So for example, you might have a situation like, let's take the heart risk patient itself, right? So you say that the robot doctor says that you are at risk of heart disease, and the patient asks why. Because even if the doctor is not able to explain in terms of absolute things, he can say things like, you are similar to patients A, B, and C, and they all had the heart attacks after having in one of these measurements. This is not as useful having sugar and BP and all that, but this is still somewhat workable. In that case, the doctor, you can have a human doctor who can go into the case histories of those patients A, B, and C and find out what about those patients caused them to have heart attacks, and then you can drill deeper. Right? So that's still a useful part of interpretability. So I think I'll not really give examples on what this. So for example, you can use these influence functions in several nice ways. For example, you can ask the question, let's say this particular image was predicted wrong. Yes, this particular image was actually labeled 7. It was labeled as 1. You can ask the question, what is the most harmful training image for this particular image? And it turns out that this is the most harmful training image. And in fact, this happens to be a label 7, but this 7 is so different from other 7. Confuse the neural model into thinking that this is not a 7. So that's, these kind of things are useful to have. And similarly, you can ask question, let's say for this particular test image was correctly labeled as, I think, the clownfish. And you can ask the question, what were the most useful training images that made you decide that this was a clownfish? And you can use influence functions to detect that these two images were what made the network decide that this particular image is likely to be a clownfish based on these two images. So yeah, this is another paradigm. This is kind of a parallel paradigm to interpreting absolutely, where you're interpreting exact features, but rather here you are attributing decisions to training data instead of absolute features. This has advantage as well as disadvantage. Disadvantage being that, for example, you might have something like, say, private data or something like that, in which case you might not be able to reveal this data to someone else. Unlike, say, this might particularly be meaningful for medical data. You can say that you are likely to get heart attack because you have high sugar and high BP, but you can't say that you are likely to get heart attack because you are similar to that person and other person, because that means that you are revealing the medical history of two other people, which might. So that's these are some other issues with these influence functions, but they serve a different purpose, and they can also be valuable in a tool set. So I think with that, I think we can wrap up. So finally, we'll end with a caveat, which is interpretability is intensely subjective. So it's not like accuracy where you can measure in an absolute sense. Okay, I think I've had a couple of questions. Okay, so here are a couple of questions. How do we deal with bias, one interpretation over the other interpretability process? Well, interpretability is the tool for dealing with bias. Bias in interpretability is going one level meta, which we will not really bother about. For example, in the case of take the leaf example, right? this is clearly a case of bias, right? So if you had the training data set bias where all the healthy leaves bright and all the disease leaves were dark. So this was clearly a case of bias. And an interpretable model with you would have debugged it. So that's something which you could do. And finally, what's your opinion on doing interpretability using GANs? Okay, so I've completely focused on supervised learning rather than unsupervised learning. So it's harder for me to say the answer. But interpretability itself is very subjective, and adding unsupervised learning, which is also subjective on top of it, is right now probably going 2 steps far. But it's okay. You can go. It's still, I think, a cutting edge area of research. Let's see. Okay, so and then Muthu asked the question: in interpretability, do we aim for a quantifiable measure of interpretability? Example, a range or the extent of interpretability achieved, something like an R squared. Not really. Interpretability is really conveying things to the human so that he can understand. It's very difficult to get a subjective measure of interpretability. You will see that you'll see in Saurabh's talk there are attempts to get subjective measures of interpretability, but they are generally very application specific. You can't have an application agnostic measure of interpretability like accuracy, where you can say this model is 70 interpretable but 50 accurate, and another model is 100 interpretable but 20 accurate. So that's not generally possible, but in very special cases you can do that. You will see examples in Saurabh's talk. Okay. So PK asked the question: for influence functions, do we assume one-to-one correspondence between test point and train point? Could the model have misclassified to use aggregate learnings from multiple images? Absolutely, you could have do that. Essentially, what it does is it assigns scalar values to each training point. Right? So for a given test point, it assigns the easiest cases. For example, the easiest case of influence functions is k-nearest neighbors. So you could have a k-nearest neighbor problem where influence functions are very natural. So you can't get an interpretable model like linear models, but you can get an influence function very easily for k-nearest neighbors. There you can see that this particular data point was classified as class 3 because it is near to these other class 3 points. So its 4 nearest neighbors are A, B, C, and D, and out of which B and C are class 3, and that's the reason why it is class 3. So that's a very natural way of influence functions, and essentially the influence function tries to emulate this instead. So it tries to get what all training points are influencing the prediction, influencing the model value at this particular test point, and you can always sort it according to highest to least and say this particular test prediction is most influenced by this training point. But of course, it is model is learning due to multiple data points and not a single data point. So don't you think in the case of doctor and patient, robot doctor gave numerical reasoning only because that is the knowledge it has? What it means how it tells him. That's exactly right, right? So that's the goal. I mean, who builds robot doctors? Robot doctors don't build by themselves, right? So we build the robot doctors. I mean, we are the robot doctor builders. So it is up to us to build in this capacity in the robot doctors to reason more meaningfully. So if you don't do that, and if you just focus on accuracy, the robot doctors will do what we have seen in that example, and they will be very accurate, but they will not be very reliable or very dependable. So you mentioned about the privacy issue. Can you do something like find similarities between features of the 2 inputs and then find out what could be the reasoning behind this? I'm not sure I completely get that question, but I think what you're asking is features of the 2 inputs and then find out what is. So this is similar to influence functions, right? So if you have influence functions, then you can go ahead and can say that this particular test point is most similar to these training points, and you can do things. So that's exactly what influence functions do, but they have other issues. That is the privacy issue, that is you can't reveal the data. I mean, for example, let's say you have, let's say people are very defensive about eating chips. Let's say that's what happens, and you've found out that this particular patient is similar to patients B and C, and let's say both patients B and C eat potato chips a lot, right? And you might not want to, you might not want to focus on, might not want to reveal that this particular patient eats chips a lot. So it's a silly example, but that perhaps that could be a reason. Yeah, so the final question is, does interpretability and model training go in cyclic? Yes, it can. Definitely it can. I mean, you can build a model first and try to interpret the model. And for example, let's say you take this example, right? So healthy versus disease. You first build a model and you try to interpret it, and you find that it is actually not finding healthy versus disease leaves, but rather it is really doing bright versus dark. In which case, it is it's not really doing what it wanted to do. So that's you should obviously go ahead and retrain the model. So you can do this in a cyclic manner. Yeah. So with that, I think we'll wrap up. Finally, we'll just go to the caveat, which is interpretability is intensely subjective, and so it might all be in the mind, right? I mean, it is very easy to hallucinate patterns when there are no patterns, especially when in the absence of something objective like accuracy. So I'll not really go and give the example here, but that's the caveat. And here are the references. So most of these pictures are from Chris Zola's blog and Distill posts, and this recent book out by Christoph Molnar on Interpretable Machine Learning. These are the references here. So I think with that, we can wrap up the session. And I think I'll hand over the session host to Ravi, because Ravi wants to make an announcement. So there are some people waiting. So how do I change host?
Okay. So thank you, Harish. That was a fantastic talk, and I hope all of you enjoyed it as I was enjoying it. So I wanted to quickly make an announcement. So RBC DSI is running our first international summit on data science and AI with invited speakers from around the globe. So one of the nice things about COVID is that people cannot travel. So it's easy to find them at home, and they're happy to participate in events like this. So this is going to be a 3-day summit with talks mostly in the afternoon. So day one, we'll have people talking on foundations of data science and AI. And even you could come and hear Harish talk about a different topic on that day, and along with other international participants. And on day two, we'll have talks on data science for healthcare, and including some of the very interesting efforts that people have been doing globally on applying AI and data science for looking at the COVID situation. And on day three, we'll talk about data science and AI applications for smart cities, manufacturing, and fintech. And very shortly, you'll find the connection information and the conference information and everything online. Right? So I just wanted to make a plug for this. So people who are enjoying the talk today, and you could get more such high quality talks in the next week.